Hello all. This video provides a quick crash course in exponentiation for complex numbers. So, in the previous video we discussed that it made sense that e to the b times I, something of that form, should look like cosine b plus I sine b. If we now want to move on and figure out what e to the a plus bi should look like, we are moving into a new number system, so we shouldn't take anything for granted, but it ends up being the case that we can apply our exponent rules and say that this should look like e to the a times e to the b I. If we make use of that, we know that e to the b I should look like cosine of b plus I sine of b. So this is going to be how we approach evaluating something that looks like e to a complex number. We find the real part, and we have e to that real part, and then find the imaginary part, fill that in over here. We'll have cosine of the imaginary part plus I sine of the imaginary part. So it's a formula enough that I should probably recopy it and put a box around it. Equals e to the a times cosine of b plus I sine of b. So that's going to be how we define something like this. So, for example, if I wanted to evaluate e to the negative 1 plus 3i, I can say, based on my formula, that this is going to look like e to the negative 1, and then times e to the 3i, which is going to look like cosine of 3 plus I. There's nothing much we can do with the cosine 3 plus I sine 3. If we really wanted to write e to the negative 1 as 1 over e, we could. How about e to the 4 plus 0i? This feels somewhat silly because this is, after all, a real number that we're raising this to. This is mostly to check that our new definition lines up with previous expectations. The formula gives us that this is e to the 4th times cosine of 0 plus I sine of 0. Cosine of 0 is 1. Sine of 0 is 0. So we end up with e to the 4th times 1, which is e to the 4th, as we would expect. And if one wanted to do this in more generality, we could confirm that e to the a plus 0i, using our new definition, just looks like e to the a. What about something that looks like 2 to the I? The reason that we turned to this, just figuring out what e to a complex number should be, is because we could rewrite this as the 2 is the same thing as e to the ln of 2. Logarithms of complex numbers get complicated, but this is just the logarithm of a real number. But we've got that to the I. So using exponential rules, we could say that this should look like e to the I times the real number ln2, which should get us by our formula. Real part is 0, so we'll have e to the 0 times cosine of natural log of 2 plus I sine of natural log of 2. Not particularly pleasant. The e to the 0th, of course, goes away. We are back to our formula that we already described. Cosine of ln2 plus I sine of ln2. We've gotten it to a point where, even though these are unpleasant numbers, we have some sense of how to deal with them. So, For your first exercise, I'd like you to apply that sort of procedure and evaluate what 4 to the 1 minus I should look like. So, now we know at least how to raise a real number to a complex power. To go further and see some of the cool geometry that's going on, we should talk about the polar form for complex numbers. So, complex number, and I'm going to draw a plus bi over here, so we'll say that this is a rather, so that assume a is negative, and then we have our b here, so this is the real axis, and this is the imaginary axis. So a and b give, in a sense, the x and y Cartesian coordinates for this point z right here. One can, of course, look at points like this in polar form, so that would be looking at r, the distance that this point is from the origin, and then theta, angle that the point makes with the positive x-axis, or in this case positive real axis. We already have a name for this distance. It's the modulus of z, so polar form we have that our radius here is going to be the same as the modulus of the imaginary number that we're trying to figure out. And then theta here, angle with the real axis. We don't have as pleasant a term for it, but if we wanted to figure out what this angle is, we've got enough right triangle trigonometry to say that the angle here, I guess since we know a and b, we know the opposite and adjacent sides, we could say that tangent of theta is going to be equal to opposite is b. Over a. There are going to be infinitely many values of theta that work, but this at least is a starting place. I said there was interesting geometry here. We already saw what happened, if I started off with something that looked like a plus bi and took its complex conjugate. That should be equivalent to reflecting over the real axis. If you'll notice, modulus shouldn't change, so modulus of z bar should just be the same as the modulus of z. However, our angle does change accordingly, so we have, I guess, that technically whatever this angle here was, instead of rotating counterclockwise as we normally do, if we rotate clockwise, we should get to the complex conjugate of our original value. So essentially we flip from positive theta to negative theta. This is all well and good. Why do we care? Let's take a look at something of the form e to the a plus bi. We figured out that this is going to look like, e to the a times cosine b plus I sine b So we would have that there. If we write this in our rectangular form, we have our real part is e to the a cosine of b, and then plus I times e to the a sine of b. So we know that if we want to find the modulus of that, that's going to be square root of real part squared plus imaginary part squared. So we'll have e to the a squared cosine squared of b plus e to the 2a sine squared of b. Factoring out the e to the 2a, we're left with the square root of cosine squared b plus sine squared b. Square root of e to the 2a is the same thing as just e to the a again. Cosine sine squared plus cosine squared, always going to be 1, so magnitude of this is always just going to be e to the a. Angle for something that looks like e to the a plus b I, we can see that essentially when we rewrote this in rectangular form, we have something that looks like, well, might as well recopy it. We knew that the tangent, or that tangent of whatever angle we've got is going to be the imaginary part, so e to the a sine b over e to the a, cosine for the real part. These cancel. We've got a sine over cosine here. That's another tangent. So tangent of theta and tangent of b are identical. We may as well take whatever b is as b, or potentially look at 2 pi plus b. Depending on our choices, we could tangent, repeats itself every pi radians. We'd need to adjust what our radius looks like in order to make things match, but yeah. So if we've got something in the form of e to the a plus bi, so if I draw a complex point here, we know we can write it as e to the a plus bi is a complex point. It has a real and imaginary part. We know that this radius here is going to be controlled by e to the a, and we know that this angle theta here is going to exactly correspond to b. So that's pretty cool. We can go, if we've got something in this form, translate pretty directly from between polar and rectangular coordinates. So, what if I want to find some powers of complex numbers? First, just to sketch this out, looking at I to the n, so if we've got I right here, we said that I squared was -1. That's going to be, I squared. I to the third was -I. And then I to the fourth power got me back to 1. As I keep on going, I'm going to keep on rotating through these 4. I said the word rotating, that's important. It's looking like as I raise my number I to various powers, what's happening is this rotation here. Let's see if I can rewrite I in its polar form. I know that the radius is just going to be 1, so e to the a is going to be equal to 1, which means that a ought to be 0. B is my angle. The angle to get to I is going to be pi over 2. So I is the same thing as e to the 0 plus I times pi over 2. So that's going to be e to the pi over 2 I. If I look at, say, e to the pi over 2I squared, that's going to be, using arithmetic rules, e to the 2 times pi over 2 times I, which is just going to be e to the pi I. Plotting e to the pi I know my radius is e to the 0, which is going to be 1. My angle is going to be pi. That puts me over here at I squared. That matches up with the work that I already did. So this exponential form tells us a lot. In particular, raising numbers to powers, we've got something interesting going on with this rotation here. Let's see if we can illustrate this with one more example before declaring anything definitively. E to the pi over 3 I to the n. I know I could rewrite this as e to the n times pi over 3 times I. So if I started off with e to the pi over 3 I in polar form, that's going to be somewhere like this with radius 1. So squaring, we see we'd have e to the 2 pi over 3I. So this here is e to the pi over 3I squared. To the third power, it'll be 3 pi over 3, which is here. I'm just going to maybe call this z. Pi over 3I. But anyway, yeah. Z to the third is right here. Z to the fourth would be angle of 4 pi over 3. So this is z to the fourth. Z to the fifth is somewhere over here. Z to the sixth is going to be the same thing as z to the 0th. Back to the real axis. So raising to powers, as long as we've got a modulus of 1, just rotates. If we've got something more complicated, then we would need to pay a little bit more attention. Let's see, we've got this e to the 3 plus 4I to the I that we want to compute. 3 plus 4I we've got our nice 3, 4, 5 triangle, so we know that our modulus of 3 plus 4i is going to be 5. So it looks like in order to get that into polar form, we would say that this is e to the modulus is 5, e to the a is 5, means that we'd have e to the ln of 5. And then plus our angle is just going to be, it's not pleasant, but tan inverse of. Opposite is going to be 4. That times I. We want to raise that to the ith power. If I multiply through, I'm going to have e to the I times ln of a, and then minus tan inverse of 4/3 right there. So we at least know how to handle these things. So again, this was now to the ith power. Things got more complicated, but we have a way of managing that. For your exercise, try this out with a very simple looking expression, except a very scary looking expression once you think a little bit more about it, but hopefully post video less scary. See if you can find what I to the I should be. Otherwise, enjoy your day.